So the talk today is going to be based on mostly a paper that I wrote with Alan. Alan should be here, allegedly. He told me that he'd be here.
Yes, he's here.
That paper is on the archive. It's published already. And then there's some future work that's happening with Magnus as well. I should say that what we're doing in this first paper, the one that's on the archive, is probably more properly called noncommutative topology rather than noncommutative geometry. It's C-star algebras, K-theory, this sort of thing. And then the new stuff with Magnus will be sort of transitioning into more noncommutative geometry proper, so with spectral triples and things like that. And so I'll try to give an indication sort of how we're getting there, but most of the talk will be sort of just non-commutative topology, you know, C-star algebras, nice stuff like that. And also, like I mentioned in the abstract, there's really just two examples I want to talk about today. And I don't want to give the impression that we are the first people to look at these examples or to understand them, but nevertheless, they're representative of what we're doing. So lots of people have worked on these examples. I've got a list here. I won't go through everyone, but I just want to give you that knowledge that, you know, this fits in the context of a lot of people's work. And if you want to see more about that in the paper's introduction, we sort of go through and outline some of that stuff. So our real contribution here is the level of generality that this is going to work for all mixing Smale spaces with totally disconnected stable set. Now, as of now, you don't need to know what mixing means, what Smale space means, what totally disconnected stable sets mean. You just want to know that we're going for the sort of increased level of generality. And then the last thing I wanted to mention is in the title, there's this Wieler solenoid mentioned. I'm not going to mention her result too much, but I just want to, you know, make explicitly clear how important this result is. This is the result that makes everything go. And so Susie Wieler was a PhD student of Ian Putnam in Victoria. So I just wanted to make sure that that result gets the credit it's due. All right, so enough overview and context. Let's go into briefly what a Smale space is, and then we'll get to our examples. So we're going to be studying topological dynamical systems. So we're looking at a metric space X, and there's going to be a homeomorphism on that, and we want to put some restraints on the behavior that we're seeing from that homeomorphism. So I'm saying it's hyperbolic. I'll be a little bit more precise in the next statement, but we're not looking for a precise definition here. We're just looking for a feel. So the idea of Smale space means that the local dynamics are very easy to describe. There's one sort of part of the set which gets pulled in towards the point and one that gets repelled out. So there's a stable attracting direction. I guess that was this in the way I did it, and one that's repelling out. And then the global dynamics can be much more interesting, but this local structure is what we mean by hyperbolic in this context. Okay, so an explicit example, this is the first one that we're going to spend a lot of time with, is we're going to build a Smale space starting with the circle and the twofold cover of the circle. So here I'm using the identification as the unit circle in the complex numbers, just so I can write down an explicit formula for the twofold cover. But you really just want to think of the twofold cover of the circle. Now, this is not a homeomorphism, right? It's a 2-to-1 map. So the typical trick of how we build a homeomorphism out of this is we use an inverse limit construction. So X is going to be this inverse limit space where I'm always using the same map between them. So we have these points here. Why not? It's going to be, say, for example, maybe it's 1. It's a perfectly good point. And then we're going to be able to specify Y1 under the constraint that it has to map, in our case, to 1. So we would have two possible choices. It could be 1 or it could be -1. And then we would continue along, and that would specify a point in our space. Now, what are the dynamics? Well, we just take G and we apply it coordinate wise. Now, this looks like maybe we haven't improved anything, but that's why I wrote this last formula here. This is using the relationship we have in the definition up here. And now we can see that this is actually going to be an invertible map and going to be a homeomorphism because we can just shift back and that's going to be the inverse of this map. Okay, now this happens to be a Smale space. It's called the two-solenoid, and it will be, you know, the example we're going to start with to try to understand these objects and what Alan and I did. Okay, so we're going to look at a fixed point. The fixed point is just 1, 1, 1, etc. And I'm going to describe what the local stable and unstable sets are in this case, just so we have a feel for how these sort of break up into those contracting and expanding directions. Okay, so for the unstable set, what we've got is we've got a point in our space X, and instead of just being close sort of with respect to the product topology, we're actually going to require that it's close with respect to, if you're familiar with it, the box topology. So we're requiring that every single coordinate is close to 1 here. Now that's much stricter than being close in the product topology. In the product topology, we'd be close, you know, maybe for the first 10 or 20 or whatever we feel like in terms of the threshold. And then the tail would be able to do whatever it wants, depending on how we've specified the metric and everything. Okay, now for the local stable set, what we've got is we've got the same sort of situation. We want the point to be close now in the product topology, but we also are going to have an additional constraint. We're specifying that the very first coordinate has to be a 1, right? So again, there are going to be lots of points that are close to the point 1, 1, 1, 1, 1 in the product topology that are not in this local stable set. And now to maybe think about why would we call this the stable set, you know, let's think about what happens when we apply the map to points in this set. Well, we apply it once, and instead of points agreeing, both being 1 at the first coordinate, at the 0th coordinate, I guess I should be more precise, then they'll agree at the 0th and the first coordinate, the way we've defined this map, right? And I keep applying the map and they'll agree on a larger and larger, sequence. And so they're getting closer and closer and closer to this point, all ones. So that's how we see that this is really a contracting action that we're seeing in that local stable set. Okay, so let's return to the general situation of a Smale space. And really, you could define these relations that I'm going to define for any homeomorphism. What the Smale space definition is getting us is that these will actually be interesting relations. So the first definition is stable equivalence, which is certainly natural enough based on what I just described, these points getting closer and closer to the point 1, 1, 1, 1, 1. So these points in general are going to be points where, remember, the 1, 1, 1 point was a fixed point. So here we're just saying we take any 2 points, and if their forward orbits eventually get closer and closer and closer together, then we're going to say those points are stably equivalent. Now, just to maybe emphasize the importance of the Smale space in this definition, imagine we had an isometric action. Then what points would be stably equivalent to each other? Well, the points would never get close together. They just stay equidistant if they were different. And we'd have no points other than, you know, the trivial diagonal would sit in there, but that would be it. So that's what I mean by we need some kind of constraint on our homeomorphism to make this equivalence relation interesting. This is the most important equivalence relation in the context of this particular talk, but I do want to mention that there are 2 more. Once we've gone in the forward direction, in the future, so to speak, dynamically, then we can also go backwards, right? So we can look at the other direction. That's the unstable equivalence relation. And then finally, we could look at the combination of both. So points that in the past and in the future tend to the same. They probably don't converge, right? But we'd have 2 points and they have the same late time behavior and early time behavior. Okay, so we have groupoids. So We want to make C-star algebras. That's how we do things, at least me. All right, so Ian Putnam, building on some work of Ruelle for the homoclinic relation, constructed C-star algebras from these groupoids. And as I said, we're most interested in the stable C-star algebra. So as soon as you make a C-star algebra, if you're me again, you want to check, a bunch of those basic properties. When is it simple? When is it going to be stably finite, say, or purely infinite? These sort of basic fundamental C-star algebraic questions. And through work of a lot of people, we have a really satisfactory answer now for this stable C-star algebra. So here, this is starting with Ian, but many people are involved. We have, and maybe don't necessarily read everything. If you want to, you can just peruse. I think the summary is this C-star algebra is C-star algebraically stable, so it absorbs the compact operators. And it's as nice as you could imagine, right? It's real rank 0, finite nuclear dimension, simple, fits within classification, all those sort of things, right? So this is a very nice C-star algebraic object. Also, maybe a key point is that we have this unital C-star algebra that we want to maybe get more access to and try and study. So we started with this non-unital C-star algebra. We know there's some unital C-star algebra in the background that all I have to do is tensor with the compacts to get my other one. What does that really look like? And can I see it maybe dynamically, right? So that's sort of a premise in here. Okay. In addition to the stable algebra, we can also have an action of the integers on this, right? This homeomorphism was used to define the relation, but it also induces an action on our C-star algebra. So I'm definitely abusing notation here by calling it phi, right? We should call it, I don't know, phi hat or something like that, but there's an induced action. And what's happening there is now we get, again, a super nice C-star algebra. Now it's purely infinite rather than stably finite. So we have, in one case, a stably finite C-star algebra. We take its cross product with the integers, and we get a purely infinite C-star algebra. This one is due to Ian Putnam and Jack Spielberg. This predates the stuff on the previous slide with the stable algebra. Now, what does this all mean? Well, the summary is we have 4 C-star algebras all related in this way, and we want to understand all these algebras. And of course, understand right now is quite vague, but what I want to do is I want to have a singular input which allows me to get access to all 4 of these algebras. So that's sort of the big picture goal of this project with Alan and now Magnus as well. And so let's look at an example so we can see where this analogy really comes from. So an explicit example of a Smale space is a shift of finite type. So I've got a particular shift of finite type here. It's just the two-sided shift on n letters. It's called the full n shift. If you've never seen it before, no big deal, right? You just have n symbols. You look at bi-infinite paths and you shift, right? So we're shifting left, but that's a choice. And now when we do this construction, this is a Smale space and we can apply our construction to this, we get as our A stable, the n infinity UHF algebra, and as O stable, we get the Kuntz algebra. And of course, it is no coincidence that the core of the Kuntz algebra is the n infinity UHF algebra. And that's exactly what we're seeing in this case. Here would be our UHF algebra. Here it would be now after tensoring of the compacts. And it sits inside here, the cross product algebra, as a subalgebra. And we want to think of it being like the core sitting inside of the Kuntz algebra, or more generally, the core sitting inside a Kuntz-Krieger algebra. So that's the way we want to think of this program. So let's return to this stable equivalence relation and look at it in this particular example of that 2 solenoid. So our circle with the twofold covering map had that inverse limit to make the space. So more, and there's that inverse limit. I'm not going to write down the map again. I think we all are fine with coordinate wise. We're applying that map G. And what are we going to try and do? We're going to try and look at stable equivalence. So here's a bunch of points that are stably equivalent to each other. I've decided to start with the point all ones and look at some points that are stably equivalent to it. And, you know, it doesn't take too much to see that these are stably equivalent to it. You start applying G to this thing and see when you can actually get the first coordinates to match up, right? That's sort of the key condition that you're looking for. And that's actually completely general. So if we look at the entire stable equivalence class of this point, it just looks like points whose first coordinate eventually are 1, right? So there's nothing special here about picking the point all ones, right? If I took another point where maybe the map's doing something more, you know, non-trivial to it, the same sort of condition applies. So I hesitate to call it a theorem, but I would call it a theorem in the slides. But this is a, you know, a little proposition that says, you know, two of these points are going to be stably equivalent if and only if you take an iterate of that first coordinate and they're equal. Okay, now what have we gained by viewing stable equivalence in this manner? Well, what we've gained is a sort of filtration on this equivalence relation, right? We have an n that we can use to specify when the y naught and of the first sequence, and then I've denoted it y hat for the second one, when they're actually equal. So this is asking for us to define a subrelation of this stable relation. So the subrelation is going to be defined to be 2 points are, I call it tilde 0 equivalent, when those first coordinates actually are equal from the start, right? And we can see that that's going to imply they're stably equivalent, but there's going to be some points that are stably equivalent that are not equivalent in this sense. Okay, so let's just make sure we're all on the same page and go through that just in a quick example. So these were our points that we previously had that are all stably equivalent, right? It's fine. Now, which of them are tilde 0 equivalent? And this is, you know, not the hardest test in the world for a reason. The point is that the tilde 0 relation is supposed to be easy, right? And it's easy to check. You just check the first coordinate, right? So easiness is good. This is a feature, not a bug, that tilde 0 is a nice, easy relation to handle. So here we have that the first and the third are now tilde 0 equivalent, and the second one, second line, they are not. Okay. So I have been slightly lying to you the whole time, unfortunately. So what actually happens is the stable groupoid that the way we define it is not a tau. And this is something that we're not too happy with. So what we're going to do is sort of a classic trick in foliation theory. We're going to restrict to a transversal, and then we will get an étale groupoid that's Morita equivalent to the one we started with. So we're really interested in this étale groupoid. So here we go. How are we going to do that? What's our transversal going to be? Well, we're going to take a fixed point of phi. Again, we want to think about this specific example of the 2 solenoid where it's just 1, 1, 1, 1, etc. And we're going to look at points that are unstably equivalent to that 1 point, right? Now, what that's going to do is shrink our space quite a lot that we're looking at the equivalence relation of stable equivalence. And that's going to allow this groupoid to be étale. So now I'm playing a little fast and loose with the topology on XUP, but let's just take a moment and think about what it is. So if you think about the Kronecker foliation on the torus, for example, you've got this line winding around, right? And you want to think of it being a line. You don't want to think of it being, you know, a dense set sitting inside this space. So an analogous thing is happening here. XUP will be dense in X, but we have a different topology that makes it a nice space. And we'll look at that in the explicit example of the 2 solenoids. So we'll get to that, don't worry. Now we can define our 2 groupoids again, now that we've cut down to this set, and both GSP and G naught P are going to be now étale groupoids. And everything that I said previously is still going to hold. G naught P is still going to, in the case of the 2 solenoid, sit inside of GSP and things like that. And we're going to be okay. Okay, so let's figure out what this XUP is for the two solenoid and figure out what these two groupoids G0P and GSP are as well. Okay, so we're going to take the fixed point, our favorite one, all ones. I should mention that in the general C-star algebraic case, you might not have fixed points, so you'd use periodic points to get around that. But this is really not a big deal for what I want to get across in my talk. So let's think about fixing this point all ones. And we're looking at XUP here, and we're going to claim that this is going to be homeomorphic to the real line. So as I've been vague about the topology, I should make that a little bit precise. So let's think about what XUP ends up being. So because it's a Smale space, it turns out it's completely determined by the local unstable set. So you remember the local unstable set was this set here where I was talking about it being with respect to sort of the box topology, right, where each of the coordinates is close to 1. And what we do is we just apply iterates to this set. And because it's the expanding direction, they expand out as we go along and start winding around the space. And that produces a topology on XUP where we've taken the subspace topology on the local unstable set. So this set here is the subspace topology. This has the topology of this union, right, when we're thinking about it like that. And you think about the line in the Kronecker foliation sort of situation, that's what you do. You take a line segment, that has the subspace topology, right? And then when you increase it, right, well, it still has the subspace topology, but as you go around, it starts getting closer and closer and closer together, right? And that's why we use this union topology on that to make it really the standard topology on R. Okay, so here it is. Let's figure out why we have that XUP is the real line. So the first step would be, what do we think this local unstable set should be? Well, if the whole thing is a line, this thing should be a little open interval. Right, so let's see how we do that. So we're going to try to identify XUP as a subset of Y. So here is Y, it is the circle, and I'm saying that, you know, depending on our epsilon, we'll have a different green shaded region here, but I'm saying that this XUP epsilon is actually can be identified as this subspace sitting inside of the circle. Here we're thinking of that circle being the first circle in this inverse limit. So let's be precise about the map I'm considering. So this is the map. We are going to take the map that takes a sequence Y0, Y1 and maps it to Y0. So Y0, of course, is certainly in the circle, and the previous point is certainly in the domain. So this is a nice enough map, of course, but you should be sort of, your spidey sense should be tingling about whether this should really be injective, right? Because Y0 should have two preimages under the twofold covering map. So how can this possibly be an injective map? And the point is, it really has to do with this constraint that we have on all the coordinates. So let's explain that. So why is this map injective? Let's look at the preimages of a point Y0 in that green region. So here we have a picture of the preimages of, say, this point Y0 here, right? One preimage is looking good. It's very close to P. And another preimage is sitting way up here, far away from P. And that's not going to give us a point in XUP comma epsilon in this local unstable. It's X, right? That'll give you a point in X, but not in this local unstable set. Okay, so hopefully we are satisfied that this is actually going to give us an interval here, and then we're going to expand out and we're going to get a copy of the real line for XUP. Okay, so now the next order of business is to understand this relation which just asks for when are the first coordinates equal to each other, right? So we now have the real line as our unit space, and we want to look at the relation we get that looks at the first coordinate. So these A's here are more useful in the second example, but I wanted to include them just to give you a feel. Each of these A's represent one copy of the circle, right? So as I go along here, this will give me one copy of the circle, one copy of the circle, one copy of the circle. And each one of these points P, Q, and R, these are all points which have first coordinate 1, right? And you can sort of visualize going around the circle, winding around, and these points here will each have the same first coordinate or 0th coordinate. Okay, so here as elements in X, here are what P, Q, and R are. So P is the point all ones. Now we have another one where we've taken 1, -1, I. Notice that in the topology on XUP, that's pretty far away from the point all ones, right? Even though they agree at that first coordinate. The green region that we had in the previous slide would appear something like here. Right? That would be the green region that we were looking at before. Okay, and in general, the relation is completely explicit. It is given by, once we've sort of scaled things right, so the integer points are occurring when we have these ones as their first coordinate. This is just 2 points are equivalent in R if their difference is an integer. So this is as good a relation as we could ever hope. And now we will describe the stable relation using this one. Okay, so first thing we do is we started with this idea of just looking at the first coordinate, but we also want to nest this, right? We had this nested idea coming from our classification of stable equivalence in terms of there's an n such that the iterates up to that threshold are equal. So that's what we mean by GKP. And let's look at this for some various K. So the first one, just the one we had on the previous slide. Now we turn it up a notch and we go to 1. So let's describe what points are equivalent here. Well, this is the points that start with 1. These are the points that start with -1. So after I apply the map once, they agree now at that first coordinate. This is 1, that's -1, and so it goes. So G2, similarly, now we've got 1 here, now we've got I here, we've got -1 here, -I, right? All these points after I apply the map twice to them will now agree on the first coordinate. So we have this sort of nested sequence of these equivalence relations, and the stable relation is completely determined by this process. So we have this open subgroupoid G naught of P. We have this nested sequence we've just described, and we've got this exhaustion type statement, right? That if we're stably equivalent, then eventually we're equivalent in this tilde K sense for some K. All right, now what kind of algebra do we have? We have the best kind of algebra. It is a type 1 C-star algebra. I'm going to say it's a Fell algebra because I don't want to make you think it's always going to be continuous trace for all examples. But in this particular example, this is a continuous trace C-star algebra. And in fact, it's just isomorphic to the continuous functions on S1 tensor the compact operators. So this is a really nice C-star algebra. And now we can ask the question, we had these 4 algebras we wanted to understand. How do I understand all these? And now I have that sort of singular input that I want to understand them with. It is this G naught P groupoid or C-star algebra associated to it. So we want to understand everything in terms of that one particular C-star algebra. So how do we do it? Here's the list of things we have. So the first thing is that the C-star algebra associated to GSP is going to be a stationary inductive limit. That's exactly coming from our groupoid inclusions and the fact that they're all actually the same relation, right, at different scales. Now for A stable, we don't get that it's stationary, right, because it's unital, but we do get that we have an inductive iteration where now we have matrix algebras. And it's a bit of a misnomer. This L, right, is changing at each matrix or at each iteration in this inductive limit. Okay. And then for our purely infinite C-star algebras, right, remember these were, the 1 and 2 were the stably finite ones. So for the purely infinite ones, what do we have? We have that this is a Kuntz-Pimsner algebra with coefficient algebra, this G naught P C-star algebra. So that's, everything now is even more analogous to the example of the Kuntz algebra, its core sitting inside it, and the Kunz-Pimsner, or Pimsner's really, original construction, right, of the Kunz algebra as a Kunz-Pimsner algebra. Okay, and what do we get for the unital version? Well, it is a Kunz-Pimsner algebra with coefficient algebra now, the unital algebra that's floating around the continuous functions on S1. All right, so what's the big picture of all this? What have we done? So big picture, we have understood everything in terms of a Morita equivalence class of a C-star algebra. So the spectrum of this continuous trace C-star algebra and a self-map on that spectrum, right? So this sounds great, right? We should, you know, go get the champagne. It's a win, right? We have solved this problem, but we should take a moment and we should think, what was the input? How did we define X? X was defined using the circle and the twofold covering map on the circle. Now, what's the spectrum of the C-star algebra we're talking about? It's S1, right? And that's really what's going on, right? So in some sense, you could feel like we've done nothing, right? The input was S1 in a map, and the output was S1 in a map. However, I don't want to undersell us too much. What we have achieved is how to extract information from that input really efficiently and really easily, right? That's the sort of take-home point in this particular example. So as an example, we can compute the K-theory of the stable algebra sort of instantly, right? We just look at this inductive limit that's stationary, and we show that the connecting map is multiplication by 2 in degree 0 and the identity in degree 1. Bang, we get these as the K-theories of the stable C-star algebra. Now for the cross product one, same deal. We got a Kunz-Pimsner model for this algebra. We throw it in the machine. It gives us a 6-term exact sequence, and we obtain the K-theories of those ones as well, right? So I want to move on to the second example I talk about, and I want to sort of show a subtlety that comes up, but how we overcome it and sort of have the same type of picture in this other example. So our space is going to be a little bit more complicated, and our map and relation, therefore, are going to be a little bit more complicated. So the space is going to be the wedge of 2 circles, and I'm being sort of vague in the slide. I'm saying that G is determined by these labelings. So I want to take a moment and just describe what I mean by that. Well, what I mean by that is this, the labels A and B are going to refer to the codomain of the map. So if it's labeled A, that refers to the outer circle. And if it's labeled B, that refers to the inner circle. And what we are doing is we're taking, say, this interval right here, it's labeled A, it's going to map to the entire outer circle. So on that little piece, it's acting pretty much like the threefold covering map, right, of S1, right? And now up here, it's labeled by A, so it's mapping, again, to the entire outer circle. So for example, this point here, this is a fixed point of this map, right? The rest of the points wrap around. And then finally, for this interval right here, it's labeled B, so something more dramatic happens. It's got to map into the inner circle, right? So it's going to map to this inner circle here. And on that, it's acting, a bit like that twofold covering map that we had before, right? That interval is getting wrapped all the way around that inner circle. Okay, so I have that on the next slide, just, explicitly, so we can think about A's are mapping to outer circle, B to inner. If you happen to be, have paper or something in front of you, a notepad or something like that, maybe just draw a circle of these 2 wedge of circles, right? And the labelings that we've got. So on the outer circle, we've got an A, and a B. And on the inner circle, we've got an A and then a B. So if you just write that down and keep it with you, I'm going to keep drawing pictures of the 2 things, but it might be helpful if you just have that in front of you while we're going along. Okay. Let's talk about what space we make. So again, we're going to apply the same method. We're going to take this, we're going to make an inverse limit. So this is completely analogous to this 2 solenoid. We just have a different space, different map, so a different X. Now, likewise, we define analogously the homeomorphism. Same deal, everything works. It's an inverse limit construction. This is a homeomorphism, and this object is called the AAB/AB solenoid. So Why is it called that? Those are the labelings, right? So if we ever forget the labelings, there they are for us. Okay, now what is XUP for this example, right? That's the fundamental question. Then we go to what is this relation on it, and then we understand the stable relation in terms of that other relation. Okay, so I'm going to say that it is also homeomorphic to the real line. Okay, so why is that the case? Again, we're playing the same game as before. If we understand the local unstable set, then we'll understand the global one. So it boils down to understanding this set right here. Notice here, in a shocking event, I don't have a typo where I put 1 still here, right? I changed it to P, right? P is the wedge point of the two circles, right? So we're saying that all the iterates are close to this wedge point. Now, we want to identify that as a subspace inside now the wedge of the two circles. So I want you to take 30 seconds, 20 seconds, whatever you feel like, and think, what green region is Robin going to show us in a second, right? We know what we should get for the two solenoid. We remember it was just a little interval around the point 1. And we also know that Robin has claimed that this is the real line, and he wouldn't lie to us, right? He would only tell us the truth. So just take a moment and think about what you think this green subset is going to be. And I will have a drink of coffee. At least you think it's coffee. And we'll be good. All right. All right, the reveal now. All right, so here is the green subset that this gets identified with. And I think the first thing you would notice is that perhaps you would guess that it shouldn't be exactly this. The first guess would be that it's a neighborhood of this point P, right? That's what we had last time. And we would have points all along here, all along here, all along here, and also along here, right? That's maybe the surprise, that we don't have points all those places. So instead of concentrating on why it's actually this green thing, what I'm going to concentrate on is why these points aren't there, right? So let's concentrate on why those points can't be there. Okay, so we look at a point sitting here, right? And we want to ask ourselves, I would like, this point is close to P, right? It's within the threshold I want of P. And I want to now continue it in a way where all the points after it are also close to this point P. So I have to look at its pre-images and not only find a point on the wedge of two circles that maps to it, but also one that is close to the point P, right? Do these pre-images exist, right, is the question. Well, how do you find pre-images under this map? Well, this point Y is on the inner circle. So we are looking for intervals labeled with A, B. And then we find 2 of them. And we see that those pre-images are actually far away from the point P that we have here. So this is one pre-image. It's far away from the point P. Here's another pre-image. It's also far away from the point P. So we cannot continue this in a manner where we get all those inequalities holding. So there is no point in XUP epsilon, right? And that's why we're at least not getting points here. And hopefully now you can sort of see how we would only get this green region here that we have. Okay, so this is now an open interval. And likewise, we get that the resulting global XUP, right, with no epsilon is going to be the real line. And now we ask the question, we're going to look at a relation obtained from equality of the first coordinates, right? That was the relation we used last time. And the relation we're going to get is now going to be a little bit more complicated. So now the A's here refer to where the points, the first point in that sequence lives, right? If it's A, it lives in the outer circle. If it's B, it lives in the inner circle. And what are the integer points? Well, they're the case where it's actually equal to that wedge point P, So let's just get that all down, right? And we notice that this P, this Q, and this R are all equivalent. All their Y naughts are equal to P. Whereas if I took this point here, this is not equivalent to a point here, right? Because they've got different labels, right? So one's on the outer circle and one's on the inner circle. Maybe like the angle is the same, right? If we are going about it, but they are not equivalent. So the equivalence relation for the non-integer points, we again need the difference to be an integer, but we have this refinement that says the labels have to match as well, right? And what's the big problem with this groupoid? Well, the problem is it is not open. This is not an étale groupoid, right? Because if I take the point Q, which I know is equivalent to the point P, there's no interval around P that is equivalent to an interval around here because the labelings here and here do not match, right? So this is sort of where Alan and I come in and we say, we want an open subrelation. Open is the most important thing. It's what made everything else work. So what do? As I said, this is not an open subrelation. We refine the relation. We break the equivalence class that we have that's causing problems, that's the integer points, into 3 equivalence classes. And what we do is we account for the labelings on either side. So we do not want P and Q to be equivalent. So we just say they're not equivalent, right? How do we do that in a systematic way? We define integer points to be the same if and only if their labels on the left and the right match with the other one, right? So you see here, this P and this P prime, the labels on the left are both B and the labels on the right are both A. So these 2 points are going to be equivalent in this new relation, but the other points, P, Q, and R, they're going to be non-equivalent points. So we've taken this one equivalence class of all integer points and we've broken it into 3 equivalence classes. What are the 3 equivalence classes? One corresponds to B on the left, A on the right. One corresponds to A on both sides, and one corresponds to A on the left and B on the right. So those are the 3 equivalence classes that we have. And this is the relation we use to make our G naught of P. This is an open subrelation, and so we can apply the machine to this. All right, so let's look at what this relation looks like. We have, again, our situation here of the labelings. I've zoomed it up a bit, and then we iterate once, and we get a relation that looks like this. Now, one thing that was also fundamentally important was that our relation exhausts, right? We have this nested sequence of relations. It needs to exhaust the entire stable equivalence relation. Now, P and Q here in this first picture, they are not equivalent, right? Because the labelings on the left and the right don't match, but they are stably equivalent, right? So it better be the case that eventually they become equivalent in our sense. Well, let's think about what happens when we apply the map once. What's happened to the labels, right? The labels all of a sudden, they match on both sides, right? Now they become B on the left, A on the right. And you'll notice that's what's happening with every single one of the integer points. So the integer points are becoming equivalent, not tilde 0 equivalent, but tilde 1 equivalent. And we still have this fact that this is going to exhaust the stable groupoid. Okay, so let's summarize what we've got in this case. Everything should be very much analogous to what we had for the 2 solenoids. So open subgroupoid, nested, right? We've got that it exhausts the stable equivalence relation. We've got now, and this is why I did not call it continuous trace in the previous one, now it is a Fell algebra, an honest Fell algebra. You know, what is the spectrum? It is a non-compact, or compact, excuse me. It is a non-Hausdorff space, right? Because we have taken that point and we've broken it into 3 equivalence classes. I didn't draw a picture of it, maybe because I got sick of drawing circles, but it's going to be 2 circles, right? And then 3 points, right? That are not going to be distinguished by the topology. And then finally, all of these GKPs are isomorphic to G naught P. And this is actually happening at the groupoid level, right? This is not anything that's based on what's happening at the C star level. Okay, so we continue, right? We now want to understand all four of these algebras now in this case. We understood them for the two solenoid. Now let's do the AAB slash AB solenoid. Okay. So what we've got again, that we have a stationary inductive limit. And again, for the Kuntz-Pimsner algebra after we tensored with the compacts case, right? Kuntz-Pimsner algebra for that Ruelle algebra. Now, what's different in the unital case? Well, the unital case is going to be more involved. We can do it in this example, and I don't want to go through it for time reasons, but I want to sort of point how this led to sort of a fundamental question that I mean, we don't really fully understand yet. It's the following question. So if I have a Fell algebra and I look at its Morita equivalence class, does it have a unital representative, right? Is there a unital C-star algebra Morita equivalent to that given C-star algebra? And in our case, you can make it, it's no problem. I mean, in our case being the AAB slash AB solenoid, you can, make it. But seeing in general how this is dynamically relevant is still a work in progress. So that's what Magnus and Alan and I are working on right now over the summer. So why was this a non-issue in the previous example in this two solenoid? Well, the two solenoid, there was a unital representative and it was canonical, right? There, if I look at the Morita equivalence class associated to the continuous functions on the circle tensor of the compacts, you better believe I'm going to take the continuous functions on S1 as the unital representative in that equivalence class. But for Fell algebras with non-Hausdorff spectrum, that's a much more subtle question, right? And that's sort of what I'm trying to get across and what came out of some of this stuff. Okay. Nevertheless, K-theory, right, works like a dream. We have a stationary inductive limit. We compute the maps in that inductive limit, and we get, in this case, because the matrix has determinant 1, this is all we really need to get that this is going to give us just Z squared. And then for the Kuntz-Pimsner algebra, likewise, we throw it in the machine. The machine tells us what we should get for the K-theories. I think in this case, in degree 0, you get another matrix. I think it has determinant -1 instead of 1, like in this example, and you compute things out. It's no problem. Okay. So I just want to get the general theorem on the board or on the slides, and then I'm pretty much done. So I'll just go through the statement of the theorems, and then we'll be done. So we have a mixing Smale space with totally disconnected stable set. The theorem, which shouldn't be a surprise, is that we have this nested sequence of open subrelations that exhaust the stable relation. We get that each of those are actually in disguise the same relation. This is just sort of happening at scale like we had with the two solenoid and the AAB-AB solenoid. And then the consequence of 1 and 2 is that we have a stationary inductive limit for this stable algebra. And then point four is where Magnus gets in on this. The first 3 are just in that paper with Alan. The fourth one is that we actually get a Kuntz-Pimsner model for that Ruelle algebra, so the cross product algebra. All right, so just a quick run through of the method. So this is where Wieler's result comes in, this really important result that I mentioned on the very first slide. She proves that any of these Smale spaces with totally disconnected stable sets is actually an inverse limit, right? And you can see through, I hope, those 2 examples, if we didn't have this, it would be over. We would not be able to start this method and do anything. So that's why I really wanted to emphasize her work in this regard. Okay, now the second thing is we know we can't take this sort of naive relation of just equality of the first coordinates, right? That's what the AAB-AB solenoid told us. So we have to refine that relation, and this is Alan and myself's sort of contribution is doing this in the full generality of this situation. Where we define this subrelation that's open. And then, once you have that open relation, things are meant to work, right? You sort of, it's nested, and you can sort of see by those examples, I hope, how everything should go. All right, now for the last thing, which is the Kuntz-Pimsner model for this Ruelle algebra, Magnus observed, and sort of been asking Kuntz-Pimsner people, you know, if they've seen this before, but if you have a stationary inductive limit and you look at the dynamics induced by this limit, it's always a Kunz-Pimsner model with the coefficients in A. So it's sort of a completely general fact. I think you might need injectivity of the stationary inductive limit, but we have that here. But this is sort of a general fact that I think people probably know, but maybe hasn't ever been written down. So if someone has a reference for that, I would certainly appreciate it. So that's sort of a quick summary of what happened in that theorem. And now what we've really done is we've taken this one Fell algebra and used it to understand the stable algebra and the Ruelle algebra. And now what the future work is to really nail down this unital representative of the equivalence class in this, I've written it as A naught. And this is where the non-commutative geometry proper happens, right? We would think about doing non-commutative geometry on A naught and lifting everything to these other algebras. And of course, people who know non-commutative geometry, it's sort of much easier, at least, to work with unital C-star algebras rather than non-unital C-star algebras when we're doing that. Also, maybe one last point is when we have these Fell algebras, you notice in this wedge of two circles examples, what we actually get is the spectrum. It's not a Hausdorff space, but it's locally Euclidean. So the fact that it's locally Euclidean means there's some sort of vestige of manifold structure floating around. So that's why we sort of believe it's amenable to this attack by non-commutative geometry. Okay, so I just want to end by thanking you all for your attention. Happy if you have questions. If not, it's all good too. Thank you.
Thank you, Robin.
Thank you.
So do we have any questions to Robin?
So, Robin, your theory, I imagine, could be extended to instead of just one homomorphism, like a group of acts on the space by homomorphism.
Yeah, so there's some results in this sort of direction. One thing we're taking advantage of is that there's really sort of just these two directions. So when you do the coordinates, sort of makes sense to go in those two different directions. What's more maybe promising for a general group would be sort of a weaker version of expansiveness. So you take some points and you look at all their iterates, right? And if they're always close together, then they actually have to be the same point. That's sort of one of the versions of expansiveness. And that would be amenable to generalization. A Smale space is always expansive, but not every expansive thing is a Smale space. So that would be one sort of way to do that or attack that.